All right, let's go ahead and get started. Just a reminder, there's a quiz due tonight, but if you have a paper copy you want to give me, I'll take it before you leave today. Otherwise, I think it's due at midnight tonight. Any questions about anything else before we get started? All right. One more thing to do on section 2.2. As I said last time, our test will cover everything up to 2.2, so we're about there. So I'm giving you a picture of a graph, not necessarily an expression that defines this function, but I want to try to construct f prime giving you this graph of f. So any ideas how I can, start chipping away at this? What can I look for? Isabel? The two, sorry, what was the first thing you said? Okay, so you're looking for where there's going to be horizontal tangents. So that's a good place to start. So where does f prime of x equal 0? So where about will, how do I know where that's going to happen? What can I look for? Where is f prime of x going to equal 0?
Whenever like the changes from increasing to decreasing.
Right. So yeah, whenever it changes from increase to decrease, and I think I see 3 places where that happens, right? So I can pretty much say that, here, here, and here, those are 3 points on the derivative, right? Okay. So now that's a really good touch point to start with, because from there you can kind of just look at what's going on around those points. So let's look at to the left of this point here. What's true about the derivative to the left of that point?
No, negative.
How do we know it's negative? This function's decreasing, right? If we want to kind of keep it in the language of graphs here, I can pick any points I want over here. And those tangents are going to be all of negative slope, right? So because of that, I can assume that, or not assume, I can say my derivative is going to do something like that. I know the derivative must reach 0 at that point I already marked here. It's going to be negative up until that point. How about between that point and the next one? It'll be positive, right? So something like that. Is it totally negative between the next 2 points? I mean, is it negative everywhere between the next 2 points? Yeah. Does it make sense that this derivative is going to be continuous the way I've assumed it is? So think about the kind of things that would cause discontinuities. Is the tangent ever going vertical? Do I have discontinuities in the function itself? Not really. I mean, I think if I look at this graph, it looks like it's continuous everywhere I've shown. So now the last thing I would worry about is to the right of that third point. What's true about the derivative over there? So is the derivative be positive or negative? And should it be getting steeper or shallower? What do you think? Right. If you can kind of imagine, if you move to the right of that point and think about what the tangent lines are going to look like, I think the further right you go of that point, you're going to have steeper and steeper tangents. So something like that. We can really do a sketch and approximation, but I think it's really valuable to kind of look at a function and think about what the derivative, how it behaves, where you can see it. Any questions about how we built this thing? Okay. So that's all for 2.2. So moving on to 2.3. So I'm pretty sure 2.3 is going to answer a lot of our being really shore a lot of things up. And what I mean by that is this. So this section is called basic differentiation formulas. So what we're going to do here is come up with a lot of different basically we're going to try to get away from that limit of the difference quotient. I mean, obviously it's pretty tedious. We're going to try to build some shorthand around that. So before we do, let's just answer this question. What does the derivative tell us about a function? So derivative is a pretty powerful thing. What does derivative tell you about a function? Anything at all that comes to mind?
Instantaneous rate of change at like a given point.
Right. So if I give the derivative of an x value, it'll tell me what the instantaneous rate of change of whatever the parent function was. Graphically speaking, like what are we looking at? Slope at a point, right? Slope of a tangent line at a point. And those are both, and hopefully you can kind of see the connection between those two things. They aren't really different, they're just kind of different manifestations of the same thing. So knowing that the rate of change is what a derivative gives you, right now I have a constant function. And I want to know what the derivative of that constant function is. And I think we talked about this a little bit on Friday. But constant is something that by definition never changes. So if I talk about the rate of change of that, what would you expect?
0.
Should be 0, right? So this is probably not going to surprise you, but if I look at this limit, so f of x plus h minus f of x all over h. What is f of x equal to for any h I can, or for any k I can think of? Or sorry, I'm getting my symbols all confused. What is f of x for any x I can think of? K, right? What's f of x plus h? Is it k plus h? It's just k, right? So think about the way a constant function works. Does not matter what input I give you of x, the output of that function is whatever this constant is. If I were to graph this thing, what would it look like? Straight line, be more specific.
Just a straight horizontal line.
Horizontal line, right? So yeah, x has no effect on this function. So whatever that y value of k is, it just holds that value for all values of x in both directions. It looks like an h. I really meant for this to say k. So because of that, I have the limit as h goes to infinity, or h goes to 0 of k minus k over h. So the limit as h approaches 0 of 0. So from there we can say this, f prime of x equals 0.
It's not a DNE, you know, if you put it apart.
So I think you got to flip your head, right? Dividing 0 by something that's not 0 is totally okay. Yeah, that's well defined. That's going to be 0 everywhere. Any questions on how we got that?
Excuse me,
Yeah.
isn't the denominator there 0 first? If you're plugging 0 for h, then you're dividing it by 0, so shouldn't.
Well, I mean, the denominator is gone at the second to last step.
Okay.
So yeah, so basically I had the limit as h approaches 0 of 0 over h. That simplifies to 0. So really the h, metaphorically speaking, doesn't have a chance to pose a problem.
So it's 0, it was like algebraically 0 over 0, right? Because k minus.
It's not 0 over 0.
0 over 0.
So it's 0 over something we know is not 0, right?
Oh,
Because we don't allow h to reach 0.
Yeah.
All right, power rules. So this is, we're gonna keep this a little bit general, but this is something really powerful that we're gonna be able to use. So basically, I'm gonna let f of x be, you know, this x to the power of n, where n is any positive integer. And then we're gonna try to find a derivative for that. And by the way, basically what we're doing here, we're proving these formulas. And after we do that, I mean, you don't ever have to go back to the limit quotient, that definition again. Basically, we're kind of building tools on top of that. So the limit as h approaches 0 of f of x plus h minus f of x all over h. What is f of x plus h in this case? Yeah, x plus h to the power of n minus x to the power of n. It's something you might have done in a previous math class, like, you know, the binomial. If you have a binomial and you raise it to any power, you know, it'd be a nightmare if you tried to expand that out and FOIL out a bunch of different pairs. So there's a theorem that kind of lets you do some shorthand, and I'll basically use that here. So because of that, this numerator is going to look pretty nasty, but that's okay. So this becomes x to the n plus x to the n minus 1 times h plus x to the n minus 2 times h squared. So basically, you know, metaphorically speaking, you can see these two powers are basically, as one counts down from n to 0, the other one's going to count up from 0 to n. And I just did 3 terms here, and I'm going to kind of abbreviate the rest, but all of these powers, like on each one of these terms, those powers are going to add up to n every time. So you're going to have a bunch of terms like this in the middle, and then I'll just write out the last 3. It'll be x cubed times h to the n minus 3 plus x squared h to the n minus 2 plus x, this is the last 4. X times h to the n minus 1 plus h to the n. So that's all that binomial expansion. And then the last thing I have to worry about is that minus x to the n that I had before. Any questions about that? Yeah, that stuff, I threw a lot of stuff at you.
What are the rules, like the power and signs?
Yeah, so let's go back. Well, hopefully this is something you've seen before. You ever seen Pascal's triangle?
Sounds familiar.
More importantly, do we know how I build all the rows of this?
No.
So basically the way you can build this triangle and just keep filling in rows forever, but basically you take 2 numbers, add them together, and that's what gets populated underneath it.
Okay.
So let's just do 1. What would the next row look like then?
10, 14, 10.
1, 5, 10, 10, 5. Go ahead.
So is this like similar to the Fibonacci sequence?
Not really.
But it looks similar.
I mean, it's just getting bigger, but they're not really related. But the reason I bring it up is if I wanted to say, like, what's x plus y to the 5th power, then what that would be is x to the 5th plus 5x to the 4th y plus 10x cubed y squared. Basically, this binomial theorem gives you it's a tool for basically multiplying those things out without having to get mired in these FOIL calculations. Go ahead.
This might be kind of stupid, but
It's
why
not.
Why are we not allowed to just distribute the n to the x plus h? that?
It's, short answer is order of operations. So where do I have space here? Let's say I had 2 plus 3 to the third. Basically what you're saying is this, that's equal to 2 to the third plus 3 to the third.
Oh. I don't think that's right. I just meant like, why do we have to do like the binomial?
So yeah, that part might not be clear, but one other thing I want to point out is, so that's not the case. We can't just, I thought that's what you were asking, and I'm sorry if that's not what it was, but the reason we expand this all out here, just like with everything else we've done, we're hoping, so right now, this is not a limit I can figure out, right? So I'm hoping that after I expand all this stuff out, I get to a place where I can. Did I get to a place where I can? Did anything cancel for me? Go ahead. So here's the good news. Everything in the numerator that didn't have an h multiplied by it is gone. It was only those two terms, but they're both gone now. So
How do you know when to stop? Because if that Pascal's triangle theorem can go on forever, how do you know when to stop the numerator?
so that's why I have the ellipsis in the middle. Really, no matter how big n gets, I mean, there is no like theoretical maximum. But what I do know is that the power on x is going to start at whatever n is and then decrease to 0. The power on h is going to start at 0 and increase to n. So I know how this thing begins. I know how it ends. I don't actually care how many of these things there are in the meantime. All right, so because I was able to do that, I can now basically divide everything in the numerator by h and simplify the way this looks a bit. So this becomes, oh, I missed a very important thing here. So there are going to be a lot of these coefficients here. And I'll just kind of insert a couple in here. I'll go back and fix this later. So when you get it from the notes, it looks better, but let's just go ahead and I'll correct it here. So I have n times x times n minus 1 plus this coefficient n2 x times n minus 2h. And then I'm going to go ahead and start skipping a bunch of stuff. X cubed times h times n minus 2, h to the n minus 2. So now that I'm doing this, can I evaluate this limit? Do you have a question?
Yeah, just for the second, that's supposed to be active violation.
It's basically, it's a coefficient. So basically the way you calculate n, that n2, that vector, this goes back to like, think back to when you did permutations, combinations, things like that. Basically that n2 is, it's a formula involving combinations. And the reason I'm going to kind of leave it at that is because that is eventually going to get annihilated. So is this a limit I can evaluate now? What's going to happen as h goes to 0? What's going to happen to all those terms that have an h? They're all going to go to 0, right? So the only thing I have left is this limit. The limit as h approaches 0 of n times x to the n minus 1. And I don't even need that limit anymore. So this right here, now basically what we've done is we have the ability to just deal with polynomials. Because if I have the derivative, if I have a function like x to the third, I know that derivative is now 3x to the 3 minus 1. So I have to go back and repair this. I'm gonna do that on my own time and I'll put it back up, but the bottom line for what we're doing is this formula here, that n times x to the n minus one. So now we can use this. If that is what that derivative is, then we can find all four of these without really going to the, and we could still use the limit definition. I don't think you want to do it for x to the power of 100. It's terrible. So based on what we just did, and I'll remind you of that here, f prime equals n times x to the n minus one. What would the derivative of x to the sixth be?
6x to the 5th.
I got to vote for 6x to the fifth. That's really what that tool allows us to do now. How about y prime here for x to the power of 1,000?
1000x to the 999.
1,000 times x to the 99. G prime of t.
4x to the third.
So close. Keep my variables. But yeah, you got it. How about h of x equals pi to the sixth?
Six I to the fifth.
Not true, not this time. Go ahead.
Zero.
Zero. Why is it zero?
This is a constant.
Because what?
The constant.
It's a constant. Pi is not a variable, just the number. So put that in there not to, I mean, yes, to trap you, but to also show you that if you see something raised to a power, don't assume that it is a variable. It's not, it might not be the thing that the function is built on. So yeah, I understand why, I mean, you could probably all see why it's tempting to say 6 pi to the fifth. Pi is just a number. And like we said at the outset, derivative of any constant is 0. How we doing? Okay. So these are the four things, or the first two are the things we just did. Derivative of a constant, any constant is equal to 0. Derivative of any term, of any x raised to a power is given by that. One thing I'll give you for free, we'll justify it later, but my proof really only justified it for, you know, whole number, positive integer powers. This power rule works for any kind of n. So it's even more powerful than we kind of built it out to be. So I'll say this. N is any rational number. Actually, it's beyond that, any real number. And then constant multiples and sum of difference, we're not going to prove these out, but these behave hopefully the way that you would expect them to. If I have x cubed and take the derivative, I can basically use the same technique to take the derivative of 5x cubed. Basically, the derivative is going to be 5 times whatever the derivative of x cubed is. We're going to do an example of that one as soon as we move on. Any questions about these four things? But now these are all basically open to you now. So everything we just did in that last example slide was, I gave you single terms, coefficients were all 1. But now that we've talked about sum and difference, that gives me the power to just deal with these terms one at a time. So let's go ahead and do that now. I want to find df dx. And we can just find the derivatives of these things individually. So what's the derivative of x to the 31st?
30.
What was that?
31x to the power of 30.
31x to the 30th. Good. How about 27x squared? Not quite 27x, 54x, because, so, let me write it like this to start with, so 27 times 2x. So the constant multiple, I mean, basically, if you want to think of it this way, you're basically ignoring the constant multiple, taking the derivative of the x term, and then multiplying it back later. 18x. Go ahead.
Just 18,
Just 18. Why is it just 18?
because x is 0.
X to 0, right? So what's the power on x now? I guess I should clarify.
Technically, one.
Right.
X to the power of 0
Yep, so yeah, 18 times 1
is 18.
times 1. Yep. Another way to think about this, if I were to, so we know we can take these things one term at a time. If I were to graph y equals 18x, what kind of thing would that be? What kind of graph would I be looking at? Saw a lot of hand gestures, but they weren't very consistent. So, what's that?
18x.
18x. It's linear, right? It's a very steep slope that cuts to the origin. If you were to draw a tangent line to y equals 18x, what would any tangent line have to have the slope of? Doesn't matter what x is. So that's why, I mean, that's why the derivative of any straight line is just a number. Because all straight lines have a constant slope, and if a derivative tells you what the slope is, the derivative better not depend on anything, just like this one does. And lastly, what's the derivative of 1? 0. So let's do one little piece of cleanup here and then we can move on. So df dx equals 31x to the 30 minus 54x plus 18. Go ahead.
And again, conceptually, looking at df over dx, that's the same as ddx, right? Like,
No, not quite. Just a refresher. This ddx operator is not really meaningful unless it operates on something. I think the analogy I used last time was the square root. If you don't place a number under a square root, it's not doing anything, right? ddx is a lot the same way. ddx implies that I'm going to take the derivative of whatever it accompanies.
okay, so because you're accompanying f of x in this.
Right,
case,
so-
okay.
That's the derivative of the function f with respect to the variable x. Question?
I was gonna ask, you can take dx as just an expression, right? There's-
Yeah, so we could also say this, ddx of x to the 31st minus 27x squared plus 18x plus 1. What's that equal to?
Same thing.
Yeah, this thing we just found. Go ahead.
And df dx is the same thing as
Absolutely, yeah. So I mean, you'll see those notation logical ways, and sometimes it'll make more sense for you to use one rather than another, but
And all of this is just a shortcut for the f of a plus h.
I promise you, I could use the limit to work through that. It would probably take me a few hours and several pages, but I could absolutely do it. But why?
Yeah.
So yeah, at this point, like, we're building up these weapons so we don't have to, get mired in all these calculations that aren't really worth the time. All right, how about this thing here? Can I find the derivative of this?
Am I?
I mean, not really. What's the problem here?
It's rational.
Rational function, right? I haven't really taught you how to deal with a function divided by another function. But does it matter?
No.
Is there something else we can do to help? What's that?
Oh, wait, maybe not. I was gonna say, because it's plain t to the 14th, t to the 5th, can you just cancel out the 5th and make it t to the 9th? T to the 8th? I know there's a way you can do that, but I don't know if you can because it's, there's pluses there, so maybe not. But
So what if I had this 1 + 2 + 3 all over 7? Can you break that up? Sure.
Oh, yeah.
Yeah.
How would you? Yeah, this is totally fine. Think about what fractions do. I am adding all the stuff together in the numerator and dividing it by the denominator. Does it matter if I divide them all and then add them? No. So because of that, and I'm going to go ahead and not write that intermediate step, but basically what I can do is this. I can divide each of those terms by t to the fifth. So like you said, t to the 14th divided by t to the fifth is t to the 9th. What would the next term be? 2t squared plus
-7.
t to the -2, and finally
-5.
t to the -5. And this is where it's going to be really valuable to understand that that power rule works for not just positive integers. First few are pretty similar to what we've done. What's the derivative of t to the 9th? 9t to the 8th. Next,
4t.
4t. And be careful. 13t to the -2.
-26t.
Ooh, careful.
To the power of negative.
To the power of -3. And it's tempting, especially at first, to think, all right, well, everything I've seen so far, taking a derivative makes the power go near to 0, right? That can be a little bit of a pitfall when you're dealing with negatives. So what would the derivative of our last guy be?
-5t to the power of -3.
-5t to the power of -6. Any questions for that? All right. So this one here, probably really hard to figure out what the graph of x looks like. Don't really have a good idea of like what cubics look like just by kind of looking at their expressions. But if we were to take a derivative of that, what would it look like? What would the expression look like? Be a parabola, right? So sometimes derivatives give you a better fighting chance to figure out kind of how a function behaves. What is f prime of x?
3x squared minus 12x. That's 11.
Just like that, right? Yeah. Can I graph the derivative? Or do I have any idea what it looks like? Give me a one-word, really rough description of what that graph looks like. It's a parabola, right? What tells you that?
X squared.
Yep, so I got a quadratic. Could probably even figure out where its vertex is, right? I'm going to say x equals 2. And negative b over 2a tells you kind of where the x coordinate of that vertex is. And if you're not aware of that, then that's fine. There are other ways to get this graph. But I mean, the big idea for me on things like this is, I mean, sometimes derivative can give you information about a function that is really hard to get to. I mean, I don't know what cubics look a lot of different ways. Parabolas, not a lot of variability with them. Your question?
Well, isn't the cubic guaranteed to go in that up formation? Because it's positive x to the third.
So it can look like that, look like that, look like that. But what do I know parabolas look like when it's y equals something x squared?
always a U.
It's one of two things, right? So that's what I'm saying. Derivatives sometimes can make a function, you know, more digestible for you. So we knew. So let's hear the red is the red of the graph of f or f prime. F prime, right? And probably knew because we just talked about it. We know that the derivative is going to be a parabola.
Is it red F?
Yeah,
Red is not red first.
F prime is blue.
Yeah.
F prime, did I not say that?
You said the opposite.
Okay, yeah, I'll give you f prime is blue. Actually, I don't feel like this matches. Oh yeah, it does. It does. I'm sorry. Because it would be a parabola opening up, right?
Mhm.
And I said the vertex was x equals 2. Okay, I feel better about that. Any other questions about? Again, it's just kind of showing you how a function and its derivative are always going to be related. All right, let's go ahead and move on. Sine and cosine. So I am showing you y equals sine or f of x equals sine of x. And I want to find f prime. So the way we're going to build this up, I think you've seen plenty of that limit quotient for today. Let's do this a little bit of a different way. I'm going to look at 5 points on here. And we're going to try to build the derivative from this graph. What can I say about the derivative of any of those points that I just labeled? Basically, 0, pi over 2, pi, and so on. X equals 0. So basically, I'm going to try to graph f prime and figure out what it is. So what can I figure out about f prime based on this graph of f? How about x equals pi over 2? We have any idea what the derivative might be there? Why do we say 0? Right, so it goes from increasing to decreasing, right? Is there anywhere else I can make that claim? 3 pi over 2, right? Anywhere else?
Every top, there's like every pi after.
Yeah, so that's going to happen every pi thereafter. So we got 2 points in our derivative. What can we say about the derivative at x equals 0? The derivative is, so the function is increasing, so the derivative is what?
Positive.
It's positive, right? I'll give you that it's positive 1. Based on that, can we say the derivative is 1 anywhere else? 2 pi, right? All right, our last point we're going to worry about is what happens at x equals pi. So I mean, the sine function is got a lot of symmetry to it. If I told you the derivative at x equals 0 was pi, sorry, at x equals 0 was 1, then the derivative at pi better be its exact opposite. So I have a function now that looks like this. Does this look familiar?
Cosine.
This is cosine. So based on this function, I can tell you that f prime of x is equal to cosine of x. The derivative of sine of x is cosine of x. Any questions? Go ahead.
Will this always hold true?
Yeah.
All right,
This is always true. I mean, we just, the derivative of sine of x is cosine of x. You have a question? No. Oh, and we'll build up to this. If it was like sine of 2x, the derivative is related to cosine of 2x, but it's not exactly. So that's something we'll build up to, but for now, we're just gonna stick with the, that inner argument being X. All right, so now, what if we go a step further? I'm giving you cosine X, what would the derivative be? Got some sine, let's see if that shakes out. So can we find the derivative at those 5 points again? What would f prime of 0 be? 0? How about f prime of pi over 2? -1, pi? Pi over 2, 3 pi over 2? +1, and then 2 pi. All right, I think I heard someone say sine. Do we agree anymore? So it's not quite sine, but hopefully you see
Inverse sign?
not inverse sine.
Cosine minus 1.
What's that?
Cosine minus 1.
No, I think it's more simple than that. If it was sine, how would you expect it to behave? When you say reverse that, what do you mean by reversing it?
Oh, secant?
Not secant. Secant is, if you saw the graph, it would look a lot different. Basically, there'd be a lot of asymptotes in it. It actually never goes between -1 and 1. I think if this were sine, I would expect it to, sine of 0 is 0. But as the angles get positive, you get positive values out, right? And then sine of pi is 0. But then the sine will go negative. So it's kind of it's reflected over the x-axis. So based on that, what is this function actually? Negative sine of x. So I got the derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. What's the derivative of negative sine of x? Negative cosine of x. And you just kind of continue on and on. Go ahead.
Second question, would sin x be integral cosine?
It's related to the integral. So I mean, there is an extra little wrinkle you have to think about when you're taking antiderivatives, where you're going the opposite way. But yeah, they're very closely related, but there's one subtle difference we'll get into. Anything else about this? Okay. So now you should be able to answer this for me relatively quickly. What is y prime?
Or sine theta?
So
Or
close.
negative sine? Maybe minus.
-4 sine theta. And again, I think we're already seeing for the most part that the constant multiples don't really, fundamentally alter what we're doing to find a derivative. Any questions on what we're doing to find that one?
So the derivative of cosine is negative sine, and the derivative of sine is cosine.
All right, find the equation of the tangent line and normal line. So let's do tangent line first. I don't think normal line is an idea we've talked about yet. So I want to find the equation of the tangent line to this curve. Y equals 3 radical x minus x. So if I want to find the equation of a tangent line, what does a tangent line have in common with the curve that it comes from?
Same 1 point.
Has that 1 point in common. So that'll be an x and y value I can say are shared. There's one other big idea that they share. Yeah, the slope. So they share a slope and they share a point. I gave you the x value at that point. They share a slope. So what can I do with this this function here to help me flesh that out a little more? Basically, how do I find the slope of that curve?
Can you just rewrite it as 3x to the power of 1/2 minus x and then take a derivative?
Yes, and in fact, I would recommend that. And it might not be obvious. But yeah, square root is a thing that power rule can reach. As long as you remember what the power associated with square root is. So if that is our function, then what is our derivative?
Is it 1/2 x to the negative one power?
Close. Gotta keep that constant multiple with me. But yeah, power rule says that I multiply by whatever the exponent was, so 1/2. And then I reduce the exponent by 1. So derivative of x to the 1/2 is 1/2 x to the negative 1/2. I started with triple that, so my derivative also needs to be triple, whatever that derivative is. What's the derivative of negative x?
-1.
-1. Question? Okay. So there's my derivative, y prime, and I'll clean it up one time. And actually, I'm going to rewrite it to probably make it easier to deal with. Now I got 3/2 radical x minus 1. So there's my derivative. Based on what I want to do, what should I do with it? What? Plug in x. So now, yeah, I want to find the derivative, but I want to restrict it to x equals 1. So that'll be 3/2 radical 1 minus 1, and that gives me 1/2, right? So I'm trying to find the equation of the tangent line. What information did that just get me? Give me the slope, right? So this is equal to n. Do I have enough information now to find the equation of the tangent line?
Technically, yes, because you could do and just substitute your known values.
Okay. So I have m, right?
Yeah.
Do I have x?
Yes.
Do I have y? I don't think we've gotten it, but we can get it, right? How do I get y? Yep. So remember, the locations are all going to come from the original definition of y. The derivative gives me rates of change, but if I want to know what the y value is here, I'm going to restrict my equation for y to only letting x be equal to 1. So I got 3 times 1 minus 1 is 2. So now I have 3 of these components. And I get 2 equals 1/2 times 1 plus b. So b should be equal to 3/2. So y equals 1/2 x plus 3/2. And I do not want to rush the normal line thing in 1 minute, so I'll go ahead and pause here. We'll do the normal line. Any questions on this? All right. Just a reminder, I have a review session on Zoom tomorrow night. I put the time in the announcements. I think it was 7 o'clock though. Yeah.